is just unlocking 3D innovation, understanding radiance fields. So with that, I think I'm just gonna go ahead and get started. So as we all may or may not know, radiance fields are a way to really create hyperreal, lifelike 3D out of standard 2D images. So this was actually a data set, which I believe is open sourced and was contained from just a standard collection of 2D images. And you can just see the level of data you can get, the amount of actual detail from the reconstruction is just incredible. So take a look at the next one. So radiance fields have really been able to transform 3D reconstruction, and some of the ways that this started was in 2020 with the first modern radiance field, which is a neural radiance field, otherwise known as a NeRF. In April of 2023, another follow-up radiance field method named 3D Gaussian Splatting for real-time radiance field rendering was released, and I'll get to in a little bit. There's also a lot of really interesting directions of which radiance fields are taking flight. And so just to reiterate, all of these methods right here, these are all different types of radiance fields. Gaussian splatting is getting a ton of attention over the last 6 months or so, but it's just another way to render a radiance field. And one other note too to really keep in mind is the actual ceiling of all these technologies is significantly higher than we are at right now. So while it might be tempting to see on either like LinkedIn or social media that there's one method that should be prioritized over another, there's really just a lot of continual innovation that we're going to see in this overarching field of radiance fields. So let's take a look at why. Why have radiance fields really been able to take the world by storm? And it's because they have a very low barrier to entry. They're very accessible because they only use standard 2D images as an input, which means you can capture them with any single camera. This can be, doesn't need to have any proprietary data or systems or functionality. This can really just be created from standard 2D images. This could be anything from a smartphone. There's some really great platforms that allow you to reconstruct a radiance field using your iPhone, or it could be ranging all the way up to more professional grade capturing systems. They're also quite efficient to be processed, where you can process a radiance field on a single consumer GPU, and the actual VRAM bottlenecks are continuing to fall, I would say, quite exponentially, where we're really starting to see quite fast and easy to train implementations of radiance fields. Another thing that's really interesting about this technology is that because you're just using 2D images as your base input, it allows you to revisit your photogrammetry data sets. So meaning that if you have existing data, you can potentially just upgrade them into getting a lifelike representation in a fairly trivial capacity. And it's also quite interesting too, is that the amount of overlapping input images that you need in a radiance field compared to photogrammetry is quite a bit less, meaning that you won't need to take quite as long in the capturing stages and store as much data as you've needed to in the past. One interesting note is that radiance fields do not currently produce polygons, and this could be changing in the short term, but the current implementations do not create any polygons, so there's no triangle-based representations. So, as I mentioned before, Gaussian splatting has really taken the world by storm, and let's take a look at some of those reasons why. A lot of them overlap with the previous slide, but just want to reiterate that Gaussian splatting is going to be the first bridge to industry adoption of these radiance field methods. And one of the reasons why this is that Gaussian splatting has the capability of rendering well into real-time rates between, starting at about 100, and I've seen it go all the way up to 900, depending on the implementation of it. And again, you do not need a specific proprietary camera system to train a radiance field. You can reconstruct purely from 2D images, and you can revisit your existing photogrammetry data sets. Again, they're lightweight and they're computationally expensive, training on consumer-grade GPUs, and the training times are continuing to really plummet. Right now, the fastest, I guess you could call implementations, you can train them in as short as 2 minutes, but I do think it's going to be overwhelmingly likely that we will see instant reconstruction times in the somewhat near future for these different methods. And so I want to just have a really quick slide because things are moving really fast, and there's this conception that the exact paradigm is going to be what goes forward in the future, but there are more and more radiance field representations that have continued to come out. We've seen a lot of research come into the world of ray tracing based approaches. So whereas Gaussian splatting, for instance, uses something called rasterization, there's a lot of papers and works like take the 3D Gaussian ray tracing from Nvidia on the left, which replaces rasterization with a ray tracing based approach. This means you're getting the access to secondary lights, as in lighting effects such as refraction, reflections. You're getting really, really clean lighting information out of it. And one that actually just was published last week that I want to highlight is called Radiant Foam. And that's where I was starting to hint at before, where we're starting to see some potentially mesh-based representation sneak back into the world of radiance fields. And this is this is as of last week, so there's not a lot of information out on this method just yet. The code comes out on Friday, so we'll see what is exactly possible from this. But it's a very exciting research direction for radiance fields. So now that we've kind of just got the baseline over, I just want to quickly show some of the ways that it's being used in AEC, and it's starting to really make its way into the world of AEC with these hyperreal visuals, their interactive renders, because again, because they render in real time, they make it very interactive. You can start to actually explore in real time. You can put spatial annotations and notes, and you also don't need the same level of input data as you did before. I don't want to go too far into this because some of the following speakers are going to talk a little bit more. These are actually two renders from two of the other speakers from today, but it's pretty astonishing the way that you can get more information out of a radiance field. So another way that I want to highlight too is how they're being used in geospatial, where you're really getting this enhanced detail preservation, whereas with photogrammetry it might really struggle a little bit to capture these highly reflective materials and thin structures, but with a radiance field you're really able to get this lifelike quality and reconstruction compared to, say, traditional photogrammetry. Another really interesting thought about radiance fields is that there's a general misconception that radiance fields are not able to take measurements, and this is not true. Radiance fields are able to be measured, and we're starting to see examples of this in the real world, and they have quite a lot of broad applications for this. There's really not one specific thing that a radiance field can be used for. Anything that a radiance field is given, it can reconstruct this with lifelike reflections and information. We can see here, here's an example from a coral reef, and the amount of use cases really are just limited by what 2D information you've captured. The last thing I want to highlight is that there's been a lot of industry momentum where we're seeing just this morning Pix4D began to support Gaussian Splatting, so as well as Cesium/Bentley, Hexagon and Esri have all introduced 3D Gaussian Splatting in some capacity, and we'll see this, I think, continue to roll out over the course of this year, where I really do believe that Gaussian Splatting is the first bridge to industry adoption of radiance fields, but I do think that this is going to continue over into the indefinite future. And the last thing that I want to highlight is these companies here are not the only ones who have been investigating this. I am now plainly aware of very large providers and companies who are also developing very similar implementations and pipelines to support various types of radiance fields, and I'm hopeful that we're going to see this over the course of this year. So, as we're talking about just some of the future of radiance fields, this is an exponential area of research right now where we're continuing to see more novel representations continue to emerge. Things that have been bottlenecks have been reduced, and we see this in this accelerated research momentum where the amount of publications that are coming out on a daily basis, it's not uncommon to see 5+ papers a day. Right now, the amount of research that's coming into this is just generally staggering and seems like it's just continuing to increase. There's also a lot of really great open source and collaboration across the community. There was just a standardization town hall a couple of weeks ago where there was just really great community effort and openness to collaboration. So I'm starting to see a lot more of the industry continue to want to work together to make this into a prioritized implementation. Some other advancements that I expect to see over the course of this year is I really do think that we're going to see very fast reconstruction time over the course of this year. There's actually specific methods that allow you to train across an infinite number of GPUs as long as you are using Nvidia hardware. So this is also a very interesting direction as well, where I really do think we're going to start to see very instantaneous reconstruction time, as well as also continuing to push the fidelity levels here. I think that already you're getting a really lifelike representation out from these radiance field models, but we are not actually close to the ceiling of this. It's actually been proven in research so far that if you were to feed it IMAX level data and you have a computer that is able to reconstruct that, you will get an IMAX level output out of this. So we are not actually close at all to the fidelity reconstruction of this. And one thing too that I really want to highlight in terms of the last year of research is compression. When Gaussian Splatting first came out, it was not uncommon to see a file size approaching well above a gigabyte, and now we are about 10 to 20 megabytes, I would say, in the last year. So the amount of compression is already 90% increase, and this is not even us hitting a ceiling for this technology. There's also a lot more tooling as well that's in development right now to create and edit this information to, and the amount of compute that's going to be necessary to process one of these radiance fields are also going to really decrease. So with all this in mind, obviously this is a very active area of research. It's very difficult to stay on top of because of how fast it is. And so that's why I have created radiancefields.com in order to catalog the progression of this technology so that everyone can stay on top of it as best as possible. So here I cover all industry stories, research breakthroughs, as well as going to be introducing some case studies to actually show the quantifiable metrics as to why radiance fields are making an impact into the industry. I also offer consulting services for any businesses that want to learn more about radiance fields and what they could be doing for their business, as well as how to start getting going with this representation. And finally, I also host a job board to reach engineers, of which I have the leading publication to actually reach a very qualified set of engineers. So next up, I believe that we have a couple more practitioners who are actually using radiance fields out in the world. So yeah, thank you so much, and I will pass it over to our next speaker.
All right, hi all. Let's see, back up. All right, today I'm talking about drone captured Gaussian splats. It's a shift in 3D visualization for AEC. I'm co-founder of Helios Visions. We're a drone services company based out of Chicago, Illinois. Some of the key features Michael also touched on a bit is the key benefits of the Gaussian splats in AEC are capturing fine details like power lines, reflective surfaces like glass and mirrors. Photogrammetry struggles with that in some instances and takes a lot longer to process. Let's see here. This here is an example of construction progress video that we captured and then created a Gaussian splat from that video. Essentially, we pulled out the frames and was able to input those frames into post-shot, and then it created this model, and then we went ahead and animated this in post-shot as well. You can see where a lot of fine details being captured there, some of the safety nets, the glass at the bottom, and some of the other fine details of that structure. This here is that same job site. This is actually a 4D time lapse, so this is multiple Gaussian splats loaded into this Godzilla Pro software. And so you'll see here that we're able to just do temporal changes, highlighting the progression of this project as it grew. You can see a lot of the power lines and other fine details, some of the trees. That would be a challenge for photogrammetry. Here you're also seeing some AI segmentation within this model. So these tools are great to be used for construction progress monitoring, communication between teams, and just general documentation of the project. You can start seeing some of the rebar there, the crane, all of those elements getting captured in fine detail. Next one here is the Elizabeth and Fulton Market. You can see this is a heavily glass-covered building, and you can see the reconstruction and reflections of that being captured in great detail. And you can also see the surrounding areas, which weren't really the subject of the capture, are also in pretty good high resolution as well. This is another example of some large-scale capture. This was also captured using drone video. This is Soldier Field. You can start seeing the texture in the trees is not just a glob like you may get with some photogrammetry models. You can see the seating and the lighting fixtures, the light poles and flag poles. Those also show up in great detail. And if you know Soldier Field or just large sports stadiums, this is just a very large structure, which when photogrammetry, it would require a lot more data and a lot more processing time to capture this, and probably a lot more locations as well, where we just, again, use the drone to capture the footage for this. You can see the lake is getting some nice reflections, and just, high quality of the surrounding areas as well. I think this was during the summer. They have a soccer field set up. This here is the Obama Library in Chicago. This is another test we were doing for large-scale captures, helping teams document construction progress. And just seeing the scale of this, along with, again, trees and reflections being recreated. This one here is the old Chicago Tribune building, which is under construction. It's soon to be a Bally's casino. This is actually in post-shot, so right after processing, you're able to interact with the model. So as opposed to just having a 3D animation, you can go through and interact with the model like this. Excuse me. You can also see where the water is being sprayed to hold down the dust. I just thought that was a pretty incredible element that was captured in the splat that I think that would have just been empty in a photogrammetry model. So again, this is a very well-known building in Chicago, and so documenting the transformation of this site, Gaussian Splat's a really great tool to do that. This here is a large infrastructure project on the CTA. This is a gantry crane. This essentially would pick up large precast pieces of concrete that you can see in the left there, on the right there. Those would be moved into place. And so you can see all the fine detail that was captured here in this model. So this is good for capturing milestones and capturing the detail that would be very challenging to capture using photogrammetry. Another example here is actually taking a previous splat that you just saw of the Elizabeth, and we brought this into 3D Studio Max and dropped in a 3D rendering and used some V-Ray to show the reflections on the building, and you can see where it's capturing the reflection of the splat that was imported into that model. You'll catch a little artifact there that looks like a cloud. So some of the key takeaways from this is that this isn't a replacement for photogrammetry. This is really a new tool to visualize and enhance photogrammetry models, or to be used on their own for visualization and communication of projects or other subject matter. It's faster, as Michael had mentioned, and getting faster every day. Way for us to capture and share these 3D environments. We're expecting wider adoption in AEC, real estate, and just overall digital twins. So looking ahead, some of the challenges that we face and some of the future potential. From our perspective, from a drone services company, we're really looking to test different types of flight patterns and different ways to capture the footage, either using photos or videos. It really depends on your use case and what output you're looking for. And also, as Michael mentioned, you're able to pull maybe other footage that you have captured already for photogrammetry and just reprocess that as a Gaussian splat. And then at the release today from Pix4D, a number of other major software vendors are also releasing Gaussian splat implementations into their software, and really cool to see that evolution. Let's see. So if you're interested in learning more, let's connect, and we'll go on to the next presentation from Ben talking about the future of Splats.
Hey everyone at GeoWeek, Ben Stocker here. Sorry I couldn't be there in person. My body decided to betray me and get sick, so I was not able to attend GeoWeek in person this year. But we're gonna do our best here with a pre-recorded session and hopefully see some cool stuff. So I'm gonna be talking about advancements in radiance fields for the built world. In general, what I want to talk about is the advancements that have happened within the past year specifically, because these have been out for a couple of years now, and just a lot of changes have happened that apply specifically to the geospatial world. So a little introduction about myself. My name is Ben Stocker, as I said. I'm a senior construction technologist at Skender. In general, I do all the research and then implementation of any new technologies that help out our project teams. And a little bit about Skender. Skender is a general contractor based out of Chicago. We handle a bunch of different markets, from interior offices to healthcare, multifamily, senior living. So we're a little bit all over the place. And so looking back to last year I did a session about Gaussian Splats in the exhibit hall theater, and we got a lot of the similar questions at the end. It was, how accurate are these? What do I actually do with this? How do I measure in this? Can I create a mesh from this? It was a lot of people trying to take this new technology and make it work with their existing workflows, things that they're used to. And at the time, there wasn't really a good answer for that. It was a lot of, oh, hopefully we'll be able to do this soon. There's a lot of people researching it, and hopefully it goes well. But at the time, we didn't have good answers. But hopefully I have some good stuff to show you here that will answer a lot of those questions. So what has changed? Now we can easily set scales within these splats. We can geolocate them. We can align repeated captures for progress. We can combine LiDAR with splats. And there's also just a lot of new editors and different point solutions that do specific things with these splats as well. So I'm gonna go through a few of them here. So first, this is what I thought made the biggest impact, and this actually happened shortly after GeoWeek last year. So reality capture for pre-training of these splats. So what I mean by pre-training is these splats start off the same way that photogrammetry does, where you start from structure from motion and you create camera positions and a sparse point cloud. And being able to do this in reality capture before bringing it to other solutions like post-shot or whatever allows us to, one, make these camera alignments much faster, significantly faster. But then you also are able to work with all the tools that are in reality capture, like scaling, geolocating, using ground control points. In the animation you see on the screen right now, I have ground control points set around this building. So this is showing all of the images that are tied to that one ground control point I have selected right there. So that alone right there is a huge advancement when creating these splats. And then, like, how's that actually beneficial? So being able to do time lapse of splats, that just becomes much easier too when you have everything aligned and geolocated. So if you do that, if you take the time to actually create them properly beforehand, doing a time lapse like you see in the video here becomes much easier. Everything aligns very nicely. A little side note, I want to point out that all of the examples I'm showing here are actually Skender projects. I'm not just showing sample data or anything. These are all Skender projects that we are working on. And then, let's see, moving on. I guess I also want to point out that in each of these little features that I'm showing off, I'm putting the software names in the bottom right corner that are used to make that workflow possible. So that kind of helps you refer to it back later or something. So that previous one, that was in Godzilla Pro to do that time lapse, and then this is in Godzilla Pro as well. So here we have segmentation AI. So it allows us to classify objects. We can put annotations on these after we've segmented them, and then it can also work like a little self-guided tour if you hover over, which you actually see in the next slide here. But in this current animation that's playing, you can see that just within a single click, I'm able to click on the columns, ductwork, some sprinkler pipe, the whole entire floor, whatever. And this is, just the workflow is single objects at a time for now, but I'm hoping that in the future, this evolves to a way where you can just, with natural language, type in, all right, show me all of the columns on this floor or whatever, and then everything gets highlighted. There are some papers that are kind of doing something similar to that already, NeRFs, language embedded radiance fields, but I haven't seen too much progress on that lately. Let's see, moving on. So this is, along with the AI segmentation, this is the self-guided tour I was talking about with the annotations. So here's a job site where we're going to be renovating all the buildings in this neighborhood area here. And so we're able to use the splat and then segment each building, and then we can add little annotations on. And this kind of works as like a tour. You can send this to someone, they can just move around, and when they hover their mouse over it, they see what we're doing with that building. Moving on then, so now I want to talk about merging point clouds with splats. So this is going to look a little bit like a sales pitch for XGrids, and I don't want it to completely, but they have really changed what we're able to do with these splats. But with their devices where they're merging the LiDAR sensor on it as well as creating the splats, these splats then become to scale, measurable. As you can see right now, it's taking a measurement. And that is huge, because before, when they were just a pretty picture or whatever, now we have these pretty pictures along with accurate data behind it. And this has been great for us. I mean, here in this particular example, this was a pre-construction walk. It was an existing client of ours that was going to be expanding into this space, and we just quickly walked through here. I think it took like 13 minutes or something to scan this whole space. And then you have a measurable splat and a deliverable that you can give to the pre-con team that they can inspect the space everywhere, take measurements wherever they want, which is really, really valuable. And another case, this is actually just from last week. I threw this one in last minute, but this was just Tuesday last week, so not even a week ago. And we're doing underground foundation work for a new multifamily building that's going up. So this was a great way to document the site, to see all of there was plumbing going in underground. Here they were pouring concrete right there where I was just taking some measurements. You can see those measurements in the distance. That's where some underground utilities were being installed. So it's really, really valuable to be able to have this type of documentation for job sites. It's a lot more advanced than just taking a 360 photo or just having an image or something, or heck, even just a normal point cloud. Because the point clouds are difficult to view sometimes. Some people still think they just look like grainy, pixelated models, where this is actually really nice to look at. You can see all the detail and still measure in it. Another thing I want to show off, so indoor splat alignment. So this was captured with the XGrid scanners and then brought into Godzilla Pro. And what I want to show off here is the ability to easily have repeatable scans to show progress. So this is actually two different captures here. You can see I'm moving them. One of them is shown as the splat, and then one of them I have showing just as that blue sparse point cloud. So you can see that these align very nicely. When I was moving them there, that was just to prove that it was two different scenes in here. So being able to have them already scaled when you capture it with a device makes it really nice to bring into platforms like Godzilla here and be able to show progress. That alignment just makes it a lot easier than having to manually align it yourself afterwards. And then I'm going to show the Splat guided tours. So this is that same site that you saw before. And it's just another new product that I've been trying out and really like a lot, called Reflect. So this was trained in post-shot and then just brought into Reflect. And what it allows you to do is just create little keyframes essentially and jump between points. This is really helpful for if you want to give this to someone who is not comfortable navigating around a 3D scene and you just want to click the little left and right arrow. You can see on the bottom of the screen capture there's little left and right arrows that's just jumping between. So it gives predetermined points to go to, and that's really helpful if you want to share this with someone and show off specific points and not just give them free reign of the entire scene. So that's been very nice as well, and I'm excited to see where this is going. I know there's some other products that are starting to do this as well, but it's taking off, and I really like where it's going. And then I think so the last thing I want to show here, merging the splat with a design model. So this was a little bit of a workaround, and I know there's multiple ways to do this now, but for this I took a Revit model into Twinmotion, then created a splat of that Revit model, and then merged the splat of the existing scene with the splat of the design model. And it makes this cool visual here where you can see what the future building is going to look like on the current site. And this obviously has a bunch of potential use cases. And I've seen some other people do some really nice workflows too, where they'll bring it into something like 3ds Max so they can actually have proper reflections in it. It's pretty incredible. So yeah, this is going to be great for just showing off to the clients, showing what their site's going to look like. Architects, I'm sure, are going to love this to make their visualizations better. Yeah, so this is only going to improve a lot, I'm sure. This is relatively early, being able to merge stuff together like this. So what's coming for the next year then? I don't really know. And that's a great thing though. I mean, something I want to point out is everything I just showed in this little presentation here didn't really exist 1 year ago. So next year, I want everything that we talked about today to look really dated. It's a really exciting space right now where things are moving really fast, new features are coming out, new capabilities, and it's really incredible to see. So man, who knows where we'll be in 1 year, but I am excited to see it. This is a really great new way of capturing our job sites, and especially now that's tying together nicely with the geospatial world. It's pretty incredible. So yeah, that's everything I had. Sorry again I couldn't be there in person, but I hope you guys have a good rest of the time at GeoWeek. Thanks.
Hey everybody, how's it going? Is anybody as cold as I am, or is it just me?
Just kicked in.
It's like colder inside than it is out in the winter in Colorado. So I'm Sean Young, and nice to see you. I want to talk. So you guys did a great presentations, all of you, and talked about radiance fields in the context of the construction site. And what I think of, like the net of what you showed, is using radiance fields for human visualization. So that's humans looking at the data. But you know, and Ben said, like, what's a year from now? What's ahead a year from now? I have this hypothesis that there's just too much data for humans. And like, you can apply that at the construction site, but you can zoom out and apply it to many other things that we all here cover. There's many other domains that we're covering in GeoWeek, right? And there's so much data. There's data from fixed cameras, there's data from LiDAR, there's data from photogrammetry, there's data now from radiance fields. And what human is going to sit, especially like in the context of satellite, et cetera, I forgot to mention satellite aerial. What human is going to sit there and watch all of these things change? And how do you get meaningful insights from this data if you're just one human? When the data is changing all the time, and there's so many sources of data. Enter AI. And AI has the ability, and specifically what's now being called agentic AI, has the ability to extract meaning from all of this data where humans might not catch that. And in the context of construction, like here's some examples of the meaning you can extract from radiance fields and other forms of data. Well, what about construction scheduling? Could an AI figure out that, hey, based on the progression report from radiance fields, we think there's going to be a delay here or there. Okay, well, an AI figures that out, and that triggers a chain of agentic AI processes. Well, if there's going to be a delay, I have another AI that's going to contact my scheduler and give them a full report in a summary, like a nice ChatGPT summary, and they're going to reschedule, or even an AI that does the rescheduling, an AI that does the recosting, an AI that's going to go back to the BIM and check to see that there's no clashes or you know, or maybe the BIM has to be adjusted based on what mistake was just made out in the site. All of these things can happen automatically. What about safety, monitoring for safety, etc. Sound an alert if, you know, if an AI predicts that based on the way the truck's backing up, the crane's moving, and this person's walking, there's about to be a, you know, major accident. It's difficult for a human to figure all this stuff out, especially with multiple sources of data. But an AI can do this, and AI can take action. So that's what I want to talk about in the context, not of construction, but I'm going to go zoom down into actually autonomous driving. The products I'm going to talk about from Nvidia today are FVDB, Feature Victor David Bravo, which is it's a way to, it's all of the Radiance Field technologies that Nvidia has been working on packaged into one toolkit, plus some AI components that help do things that Ben was talking about, which is object detection, segmentation, classification. And it's for software developers, it's not for end users. So if you're a software developer, this is something to help you accelerate. I'll talk about Omniverse, I'll talk about Earth 2 and Nvidia Cosmos. I'm not going to pitch these products, just underlying the concepts I'm talking about. Okay, so in the context of autonomous driving, we want to train an AI to navigate around the real world. And one way to do it is to go and get data from the real world. And as a matter of fact, you really want to have ground truth data from like a LiDAR of the real world, and that's why you see all these cars driving around with LiDAR rigs on top. But there's a problem. One, you have to have cars driving everywhere, and that's a lot of cars doing a lot of driving. Two, cars driving around capturing LiDAR only capture one specific moment of time. So it could be summer, it could be winter, it could be with traffic, it could be without traffic, it could be no pedestrians on the street. But if you want to train an AI, you have to train an AI on that precise location, like that complex intersection, with all these different scenarios, during the day, during the night. And who's going to actually, like, you know, stage a real world data capture moment where you have a kid jumping in front of a car to chase a ball? You don't want to do that. So you do what's called synthetic data, training in the synthetic environment. And that's what you're looking at here. And to do that, we build digital twins. And this is a digital twin that was built in Omniverse. And then you drive the virtual car around, and you create all of these simulated scenarios that are based on the ground truth of data captured, but you have enough variation in the time of day, in the season, in these different simulations that the AI actually learns how to drive a car for this specific area. Now the key to this is the synthetic environment needs to be as accurate physically as the real world, because if it doesn't behave like the real world in the simulated environment, the AI brain goes into the car, now it's going to make mistakes because it wasn't trained in the right class, in the right style. Okay, how do we do this? Now, one challenge about doing this all in digital twin, it's a lot of work, and you want to have the ground truth. So how do you get the ground truth? Well, you get the ground truth by starting in the car and getting the LiDAR data. Now, LiDAR today, Radiance Fields tomorrow, or maybe a mix of both. And what you're seeing here is a car driving, but with and using LiDAR, but with features automatically extracted using segmentation, auto segmentation. Now, I want to just pause a little bit in the spirit of what Ben was doing in helping you understand the software. Hexagon Cyclone 3DR, it's in the Expo, has the ability to do what's called auto classification. So it has a few different models for different scenarios, like construction, indoor, outdoor, general, and it identifies trees, roadways, etc. Just like you see here, the AI is identifying lane markings. You can do similar things inside of Esri ArcGIS with what's called GeoAI. Has anybody tried either GeoAI or, yeah, Mark, you have, but anybody else? Or Cyclone 3DR auto classification? Anyone? I strongly recommend, if you want to get started with AI in the context of reality capture and satellite imagery, those are the best, easiest ways, because they just work right on your desktop. Just need the software and you're go, and of course, data. So we're identifying data here that helps us accelerate the process of learning. What's interesting is also what you see here is now we're creating a 3D mesh from the data. Why is that useful? Because if you have a car driving down the street doing LiDAR capture, and we know where the line markings are, we know where the curbs are, we know where the buildings are, we know where the trees are, but we want to create, remember I was talking about scenarios. So we want to create different scenarios. So we want to, number one, convert that all into a mesh. Now we have basic geometry we can play with. Now, with that mesh, we can change the trees out. They were low poly trees from the LiDAR scan. You heard from the guys earlier that that's a consequence of doing LiDAR. You don't get beautiful trees. So you could replace those trees by segmenting them, identifying them, and replace them with high quality tree proxies. You could start putting cars everywhere and creating all these different simulated scenarios. You're not stuck with what you scanned, but you have the accuracy of what you scan, which is the ground truth of that specific street and that specific intersection. Now you can start building all these scenarios that I'm talking about using AI. So what you're seeing here is somebody typing in saying, I want to build this traffic simulation. So take a street that had no construction simulation. Take a street that had no construction on it at all. It was scanned with no construction. Now using AI, I search through my 3D model library and I start adding pylons and construction signs and construction workers that are pre-rigged to animate. And now I can synthetically create a construction simulation on that same street to train an AI. Instead of having to go get a car to find, or hire a bunch of construction actors, which is never going to happen on a busy street. This is how you do synthetic data. And this applies to multiple use cases, not just autonomous driving. You could even have the AI understand the context enough of the street to actually place the geometries for you in the right place. It knows the pylons go on the ground level. And now they can even animate the scenario. The AI can animate the scenario by itself and create all kinds of permutations of that scenario, which is called domain randomization. AI needs a lot of data. What you saw there before was 3 different cameras. We need to simulate each of the cameras. So there's whatever sensors are on the car need to be simulated. And you saw also simulating in the day, in the night, in winter, in summer, etc. To train an AI, you need tons and tons of imagery. So what I just showed you leading up to now was doing all this in the context of the 3D digital twin, which in our world, and Nvidia's world, is based on Omniverse. And all of the different scenarios need to be done by creating new 3D models or 3D scenes in that digital twin. But there's yet another way, another layer to make this go even faster and even more realistic. And this is with, you've heard of LLMs, large language models. Well, now we have something called VLMs, which are video or visual language models, which is very much the same thing, except it produces videos. The input in this case for the video AI generation is the 3D model. So here's what this looks like. We feed the AI, in this case called Cosmos, the Omniverse 3D simulations. Could be in the form of a video rendering. The AI then takes that, and even if it's a rough rendering, the AI then makes it look like a real video. And the AI that can then create multiple permutations. The AI can then do day and night and winter and summer without us having to do that inside of the digital twin. I know this is getting a little trippy. So, when you have, sorry, I'm missing a slide. Let me try that again. Okay, so yeah, I guess I'm just missing some video. So you go from 3D as an input, you feed that into the VLM, or in this case Cosmos, say, take that video and make multiple permutations, day, night, winter, summer, lots of pedestrians, not a lot of pedestrians, and the Cosmos model. Cosmos is a VLM that's trained on physics, does that in a physically accurate way. When you have that model, you can also use it, and here's an example in the a construction site or traffic, you can have the model connected to a real-world camera, and the real-world camera, now this is coming back to the construction site, the AI is monitoring the real-world camera and telling you what's going on. Like there's been an accident at this intersection, or somebody just fell and hurt their leg. Sorry, I'm struggling with my videos here. So you could search inside video in a similar way. So this is AI understanding exactly what it's seeing in the video, because this AI has been trained on the type of synthetic data that I showed you. And if you're interested in trying out Cosmos, if you scan this QR code, you can go and play around with it. There's video preloaded, and you can start asking it questions, and I think you can load your own videos and stuff like that. Okay, I'll just pause a little bit longer. Okay, now let's zoom out to the whole world and see how does this apply in the geospatial context. And it's very similar concept. Here we're creating a digital twin not of the city for cars, but of the whole Earth to understand weather and climate change and the impact on the ground. Using AI, we've trained, in this case, something called CoreDiff, which Nvidia has trained a weather model that predicts the weather, predicts the path of a typhoon, for example. And we can simulate this prediction in the atmospherics and bring it down to the ground level. Now, where this gets really interesting is now using the same process I just talked about, we want to be able to create, to train an AI to understand what is the impact of a certain climate effect, like a typhoon, on the ground. So if it strikes at this part of the ground, like in this city, is there going to be flooding? Is there going to be mudslides? Which specific area is going to be impacted? Should we dispatch emergency resources, etc.? You do that process of training an AI to understand what the prediction of the future, the same methodology is used as what I described for training AIs to drive cars. You create synthetic data, you simulate all these different scenarios, AI eventually learns physics, how to drive a car, or what's going to happen on the ground if there's a typhoon in terms of flooding. That's my talk. Thank you. I think we're supposed to all sit down here and have a little chat.
Good catch. I think they're all on.
They're all on?
Physical.
Okay. You want to be the MC?
Sure. So yeah, I can, I guess, be the moderator for this. And yeah, no, so we definitely saw a lot of really incredible construction use cases for Radiance Fields and hyperreal 3D. I'm definitely curious to chat about like how it's potentially sped up like your workflow or been able to really help translate what an on-site location looks like to any stakeholder that needs to see it.
Yeah, definitely. From a 3D visualization standpoint, it's sped up the data capture process, like he was mentioning before as well, with overlap. There's not as much overlap as required to create these visualizations. We're also able to use footage that was captured just for regular video purposes and use that footage to process into the 3D splats. And so it's really sped up the process, not only in capturing, but also in processing the visualizations.
Yeah, it's been pretty cool as well. One of the things that I want to highlight a bit more too is the extensions of which you can build on top of Radiance Fields, because while Radiance Fields are not the most AI intensive application, they are able to be used in conjunction with more traditional AI systems like an LLM, like you were showing, Sean. And so one of the things that I really want to be able to discuss and bring up is that the actual lifelike visualizations in some ways are going to be the most simple ways that you can utilize a Radiance Field, where you can start to really put forth a lot more stronger innovation is to actually bring in these AI systems to have them understand the data that actually is occurring in the real world. Because when you take one of these reconstructions, it's really being built off of just existing real world 2D data, and you can actually start to create some level of automation, like you were saying, comparing with certain construction schedules, timelines, simulations, where there is a very cool paper that Sean mentioned called FVDB from Nvidia, where it essentially is just a very powerful ingestion engine where it's able to take in just very multimodal data and start to really train very large-scale radiance fields on the size of cities. So far, the largest radiance field I've been able to see has been 25 kilometers large, and I forget how many hundreds of thousands of images that went into training that single radiance field. But that is not an actual cap. That was a cap that was introduced artificially because it was the amount of GPUs that they had access to. But you will have the ability to create very, very large-scale radiance fields should you have the GPUs as well as the input images to reconstruct them. So I know this is a bit of a rant, but one of the things I just wanted to highlight is there's quite a lot of ways to utilize radiance fields in some capacity, whether it's just visualizing, translating information in a more three-dimensional way, or really starting to supercharge some of these pipelines with the current state of the art in computer vision.
We're also, we should take questions from the audience at
Yes.
some point, right?
Yeah, so I guess if people have, I think there's a microphone right here in the center. I don't know if that might be easier, just so that we could.
Or you could yell.
Yeah.
I'm Lyra. I was wondering if you could repeat the name of the engine that you utilize, the Nvidia engine that you just mentioned?
Sure. So that method is called F as in Frank, VDB, Victor, Delta, Bravo, and it's currently still, I think, in like a research preview. I mean, I'm not, at Nvidia, so I can't.
It's in early access. If you just Google FVDB, it should show up as your first thing, and you just scroll to the bottom of the page and click on access or early access program and sign up. And if you need help implementing it, if you're a software development team, just ask Michael. He'll help you.
Any other questions? Otherwise, I can just keep asking some. Oh, good.
You were mentioning briefly about scale, because most of the examples are very small scale, virtual scale, like 25 square kilometers. What do you think are the biggest challenges to being able to scale to a couple hundred square miles or something?
So I think that in my opinion, it would be just getting that actual data that, all assembled and then just having the compute to run that, where the requirements to process these are continuing to plummet, I would say. It still is just, you will need a pretty powerful system to do that reconstruction. But the research has shown that it will reconstruct, assuming that the data is captured in the correct way. But if you're capturing it in a standard photogrammetry pattern, it more than likely will work.
Are you seeing even a smaller scale, as you start to scale up, are you seeing more artifacts or other issues with accuracy?
Not necessarily. There's not necessarily that risk right now. There are only a handful of data sets that have been opened for evaluating that. So in some ways, it's still somewhat of an open-ended question. But from what I can tell, some ways that people do it now, for instance, is they might train very large areas and then merge them separately thereafter. But if you want to train everything in one go, there's just a handful of methods right now that will allow you to do that. But I expect that it won't be an issue. One other thing that you could actually point to with this is from Ben's examples with X-grids. I've been able to test their scanners for quite a bit, and just walking around Manhattan and reconstructing a couple city blocks. It's not very difficult. You just kind of passively walk around the city, and then everything is just you just need to have the compute to process it, and everything is to scale still.
Doesn't the radiance field make up elements of the model though that it can't see? Is there how do you handle that if you're trying to be really sure that what you're measuring or the changes you're seeing are real?
Yeah, so essentially, I think what you're referring to there's floaters or artifacts that kind of look like a little hazy. Radiance fields, as because there's no generative world in the straight radiance fields can be generated, but in the just vanilla implementations of them, it won't actually hallucinate any information that's not there. It might just translate as noise. But where you can start to really supplement that is with using something like X-grid scanners, or starting to pair it with LiDAR so that you're actually getting all of these views. And the more deeply that you start to investigate these capture principles, you start to really be able to effectively cut out the artifacts. I would say it's fairly easy to understand how, like once you really start to tune in your cameras and setup, it's fairly easy to get blur-free data from it.
So you're saying you have to capture everything in its completeness in order to have a perfectly accurate model.
Typically, yes, but it just depends on what if you want to do it with like your iPhone, for instance, or if you want to do it with a DSLR, then typically that's the way to do it. But if you're really needing precise information, pairing it with a LiDAR system or something like that really makes it a lot. It becomes way less of a consideration. It becomes much more of a passive, walk through the site that you need to capture.
What about an area that's shadowed though by both the LiDAR and the camera? Will it fill that in artificially, or will it leave it as a blank space?
That's a good question. I think I've seen like both of those situations happen, where sometimes it just will just fade to black, and you can still explore it, but there won't be any information there. And I've also seen it where sometimes it'll start to pull just like artifacts into that. But I think it's more dependent on the space, and if there's like a complete lack of light too. One other interesting way to do this is that radiance fields are able to be processed with different camera sensors and different camera types. So in the case where there is no visible light, perhaps reconstructing a radiance field with a different method will be beneficial.
So I heard you say the magic words: combine the radiance field or the Gaussian with the LiDAR. Is there a way for those of us that want to experiment with that? Is there recommended software?
So right now, I would say, okay, well, so if you want to experiment with Radiance Field plus LiDAR, definitely I'd say the industry leader is X-Grids, and I know that they have a booth just downstairs. They have a couple, I think, demos too. I would suggest just checking out some of their solutions. I think they're probably the leader right now.
Any other questions? So I'll ask you guys a question. Because as Ben said, is LiDAR photogrammetry, he kind of had a little bit of a question mark. Is it going away? And what about mesh? Do we need it? So what do you guys think? Like, what does the future look like with respect to reality capture? Is it going to be photogrammetry, LiDAR, or is it going to be radiance fields? And do we even need a mesh?
Well, it's very interesting because there was that paper, Radiant Foam, that just came out last week, and I think that might, it remains to be seen exactly what that allows for and what that mesh reconstruction capabilities are. Though there has been a lot of progress in the world of mesh reconstruction capabilities for Gaussian splatting. There's a really cool paper called 2D Gaussian splatting, where essentially it changes out the 3D ellipsoids for 2D circles, and you start to get a lot cleaner meshes out of it. In terms of comparing it to say like photogrammetry or some of these other technologies, I do think that the technological ceiling of radiance fields is still nowhere close to being fully exploited. So it's going to be very interesting to see what research comes out both on the academic level as well as industry to, one thing actually that I'd like to point out too is with like Pix4D, for instance, today, they have the ability to toggle between back and forth in a pretty seamless way. So it's like training one method doesn't invalidate you being able to use the other. So you're going to be able to, you are able to flip back and forth depending on what your individual use case is. Though in the future, I do expect these radiance field representations to get very powerful, and we'll see what happens with that.
Okay, follow-up question. For most users here, do you expect that they need to get into the type of research that you guys are doing in terms of reading all the research papers and all that, or do you expect they're going to get their radiance field technology and the Pix4D and all the other software that they're using today?
Yeah, it's another great question. I think that we're going to see a confluence of both of these things, where I do expect a lot of these major platforms and providers to offer some form of Radiance Field solution. But that said, there's also a lot of really great open source repositories where you can get a much larger head start and really be able to fine tune some of these things. The example that I would give here is NeRF Studio. It really is a very modular way to build on top of these platforms and really customize them to your needs. Obviously, this is a bit more of an engineering lift compared to, say, using a company like Pix4D or Bentley. But this could also be a really great option for people who really need some specific parameters to be tuned. And this is just existence right now. I also expect that we will see more open source repositories that are similar to this, that really allow you to more modularize your needs related to the world of hyperreal 3D capture.
Ted, when you showed that image of the ray traced skyscraper, to me, that is so exciting. By the way, that was on social media. Was that your? So Chaos Group promoted that quite well. Yeah, congratulations. So very exciting to see like a major rendering application like we already have Gaussian Splats for ray tracing. But to me, this also kind of like, I mean, we've all seen those 3D animations of cities in the video games and the Pixar movies and whatnot. I think it's about to get like a whole lot more real, right?
Yeah, definitely, especially with the architectural renderings. A lot of times we're limited to like grayscale building shapes and things like that. And with how fast, especially Fulton Market, where we're located, where that was captured, that's changing weekly. So, that any captured footage goes out of date pretty quickly. And so be able to have real world representation for permitting and community meetings and for architectural renderings is really great.
Yeah, and I guess quickly to add on the ray tracing side, definitely pay attention to what happens in the form of ray traced radiance fields. There's a really cool, two really cool papers actually from Nvidia. One is called 3D Gaussian Unscented Transform, which brings ray traced effects into rasterization, which is just very crazy, and as well as 3D Gaussian ray tracing, both of which Nvidia has said that they will open source at some point. But I would definitely pay attention to these two extensions to the world of radiance fields.
I think we're at time. Are we at time? We have time for, I have no big plans, so if you guys want to ask questions, go ahead. Yeah.
I had a question about surface aligned Gaussian splatting.